Recall that by convention in Unix, processes expect to inherit two standard open file descriptors. File descriptor 0, which we call standard in, for reading from a terminal, and file descriptor 1 called standard out for writing to that same terminal. Your shell is no exception, so it should both have standard in and standard out. This means then when our shell spawns off other processes, when you run a command, then those commands expect to inherit standard in and standard out. However, while processes normally expect standard in and standard out to be open to a terminal, it is sometimes useful to give a process something other than a terminal for its standard in or standard out, and this is called redirection. Assuming you start with a program like the shell that has its standard in and standard out open to a terminal and to the same terminal, well, if that program is then going to spawn off another program by forking itself and then in the fork executing the new program, well, after the fork but before the exec, it should close either standard in or standard out or both, and then open one or two other files, which will then take over the file descriptor 0 and 1. Because when you open a file in Unix, it's going to use the first available file descriptor number. So if you close, say, file descriptor 0 standard in, and then open another file immediately after, you know that it's going to be open on file descriptor 0. So what redirection allows is that when the shell spawns off another program, that other program, maybe its standard in is still reading from the terminal, but its standard out is writing to some other file, or vice versa, maybe it's still writing to that terminal, but reading its standard input from some other file, or alternatively, maybe its standard in and standard out have both been redirected to some other file, or finally, maybe the standard in and standard out have both been redirected, but to separate files. So to give a very simple example of how this might be useful, say we have a program which normally prints some information on the terminal, that is, it writes to standard out. Well, if we redirect standard out, then the program will, instead of printing to the terminal, will print to some other file. It'll write the data to some other file. Which, might be useful because maybe you don't want to read the data right then, you want to preserve it in a file and read it later, or something along those lines. Whatever your purpose, we can redirect standard in and or standard output with any command in the shell using the special characters, the less than sign and the greater than sign. If in a command you see an unquoted less than sign, that less than sign should be then followed by a file path. And what this tells the shell to do is to redirect standard input by closing file descriptor 0 and then immediately after opening the specified file for reading. Effectively then that file assumes file descriptor 0 and the inheriting program is none the wiser. It reads from standard input with the assumption that it's whatever file it's supposed to be. Likewise, an unquoted greater than sign should be followed by a file path, and this tells the shell that when it executes the command to first close file descriptor 1, standard output, and immediately then open the specified file for writing, so that it assumes file descriptor 1. Now, these redirections can actually be specified pretty much anywhere in the command. You can put them actually even before the name of the command, though that would be an odd thing to do. I personally prefer to put them after all of the program arguments. I find it misleading and confusing if you place them anywhere else because it seems to imply that they're somehow a kind of argument when they're not. These are not arguments to the program. They're a special trick that the shell does before it even launches the program. So here, for example, we invoke the command foo, and it has two arguments. First, a string reading bar and another string reading 3.5. And the command includes redirections both for standard in and standard out. The order in which you write them doesn't matter, but here I've placed the redirection of standard in first. So this is redirecting standard in to a file called notes.txt, and it's redirecting standard out to the file /dev/null, which recall is a special Unix file which when you write to, the data you write just gets discarded. This should explain now why standard in and standard out are separate file descriptors. Because if we just had one file descriptor to both read and write from, then we couldn't redirect them independently. But by having separate file descriptors, we can redirect them independently. Redirection in Unix makes possible another trick called pipelining. When in the shell, we separate two commands with the pipe character, which is usually found on the same key as your / key. It's easy to mistake for a lowercase l, but it's not. It's a separate character. It's just a vertical bar. The shell will run these two commands in parallel. It will run them at the same time, and it will redirect the standard output of the first command, which in turn is read as standard input of the second command. Effectively, whatever the first command writes to standard output gets read as standard input by the second command. The reason we have to involve a pipe is because processes can't read and write from each other like files. Processes simply can't do that, so we have to put a pipe in the middle. Looking at exactly what happens here, first the shell creates a pipe to connect the two processes, and then the shell forks itself actually twice, and then the parent, the original shell process, waits for both of those children, it waits for both of them to complete, and then in one of the child processes, it redirects its standard output to the pipe, the newly created pipe, before it then execs the first command. Meanwhile, the other child process redirects its standard input to the pipe before it execs the second command. So again, these two commands execute in parallel, they're separate processes, and the original shell process waits for both of them to terminate before it continues on its business. When we pipe commands, we're not limited to piping just two commands together, we can pipe three or more. In the case of three commands, you'd end up with something like this, where the first command writes its standard output to a pipe, and then that pipe is read as standard input by the second command, which in turn writes its standard output to a second pipe, which is read as standard input by the third command. So here, when we have three commands connected by two pipes, that actually represents two pipe files. Again, be clear that all of these commands connected by pipes are run in tandem, they're run in parallel, and the shell waits for all three to finish before it continues. So moving forward, we need to be clear on terminology. What in the shell we call a pipeline refers either to just a single process executed on its own, or it refers to multiple commands separated by the pipe character and therefore executed in tandem connected by pipes. What we call a command list is one or more pipelines separated and terminated by the semicolon character, ampersand characters, and or the new line character. So most commonly when we type commands interactively in the shell, we terminate each pipeline by simply typing enter, that is, inserting a new line character, and then the shell executes that pipeline. We can also write multiple pipelines which are meant to be executed one after the other by writing them all out separated by semicolons before hitting enter. Here, for example, we have two pipelines, the first consisting of just the command ls, and the second consisting of just the command cat. Cat is a standard Unix command, which in this case will print out the content of the notes.txt file to standard output. But in any case, what happens here is that the shell will execute the first pipeline first, wait for it to finish, and then execute the second pipeline. So ll will run and complete first before the shell executes cat. So the important thing here is the distinction between semicolon and the pipe character. Here, when we write foo, bar, fizz, buzz separated by semicolons, that executes all these commands in sequence, one before the other. If though we were to separate them all with pipes, this not only connects them together with pipes, it also runs them in tandem. If we change the middle pipe here to a semicolon, now this is two separate pipelines. Foo and bar run first, and then when they complete, the shell runs fizz and buzz. I mentioned in passing that a pipeline can be terminated with an ampersand, but the significance of that we'll discuss a bit later. Somewhat analogous to the way functions return values, every command in the shell returns what's called an exit status, or sometimes exit code. The exit status is always an integer, and by convention the value 0 is used to denote that the command completed successfully without error, while any value other than 0 by convention indicates some kind of error. What that error is exactly depends upon the particular program. So if you run a program and get back a non-zero exit status, you should go and look in that program's documentation to figure out what it's supposed to mean. You may be wondering where a command's exit status comes from. Well, if you recall back to our discussion of system calls, there was a system call called exit to which we would pass a number. That number we pass to the exit system call is the exit status returned by the program. When a parent process invokes the wait system call to wait for one of its children, what wait returns is the exit status from that child. So it's the shell which collects the exit statuses of any commands you run. So the question now is, for me, the user of the shell, what can I do with these exit statuses? Well, one thing we might do is connect two pipelines with a pair of ampersands or a pair of pipe symbols. With the pair of ampersands, the shell will first run pipeline A, and then if the last command of A returns the exit status 0, then the shell will run pipeline B. Otherwise, if the last command of pipeline A returns something other than 0, then the shell will not run pipeline B. It will get skipped over. So the execution of pipeline B here effectively becomes conditional upon the successful execution of pipeline A. The double pipe connector works exactly the same, except it inverts the logic, such that pipeline B will only run if the last command of pipeline A only returns something other than 0. If instead it returns 0, then pipeline B gets skipped over, it doesn't get executed. So here, for example, foo is executed, and if its exit status is 0, then bar is executed, otherwise it's skipped over. Then whether or not bar ran or not, the fizz command is executed because it's separated by a semicolon. The semicolon here has a lower precedence than either the double ampersand or the double pipe. So you can sort of think of it as if there are parentheses around the first two commands here and the second two commands. Though I don't mean that in a literal sense, because we don't use parentheses exactly like that in the shell. They don't group commands in the same way as you group expressions. But in any case, so the fizz command here will run, and if it returns something other than 0, then the buzz command will return. Otherwise, if fizz does return 0, then buzz will not run. So the double ampersand and the double pipe, those are two ways you can utilize return codes. As we'll see mainly in the supplement, there are other ways of using exit statuses. So far, I've only discussed what I call process commands, commands which are actually executable programs. There's another kind of command, however, called a built-in command, which is a command implemented in the shell itself. So when we execute a built-in command, that just runs as code in the shell itself. There's no spawned-off process. As we'll get into, though, there's what we call a subshell, which is essentially a fork of the process, and in some cases you may end up running a built-in command that runs not in the main shell process, but possibly in a fork of the shell. Also, while these built-in commands do run in the shell, they still do allow for redirection and piping. When a built-in command is redirected, the shell doesn't actually redirect its own standard input and output, but just for the sake of that one built-in command, it will arrange things to get the same end result. Basically what happens is that every built-in command is given a duplicate of the standard in and standard out file descriptors, and then if you redirect the command for the built-in, then that duplicate for that just one built-in command is redirected, and so it doesn't affect any other commands, just that one command. How exactly this is done is of course an implementation detail of the shell, which you don't really need to concern yourself with. In any case, Bash has about 70 different built-in commands, and the first one we'll discuss is the help command. The help command simply prints out the standard output information on how to use the built-in commands, including the help command itself. So if at the shell you type help and hit enter, you'll get this list of all of the built-in commands, and if you want more detail on one of these commands, you simply type help, space, and then the name of that command and hit enter, and then the help command will print out detailed information of whatever command you specify. Be clear that the help command only gives information on the shell's built-ins. It doesn't give any information on regular Unix utilities, like say the ls program. If you want to see documentation for standard Unix utilities like ls, there's a standard Unix utility for that purpose called man, as in manual, short for manual. We'll talk about how to use man in the supplement. Another built-in command is cd, which is short for change directory. And what it does is it sets the current working directory, or the process working directory as it's sometimes called, of the shell process itself. And so it should be apparent why this is a built-in command and not just a standard Unix utility, why it's not a separate program, because separate processes can't modify the shell's current working directory, only the shell process itself can do that. This is an important thing to keep in mind because in some contexts, as I mentioned, built-in commands get run not in the shell itself, but in a subshell that is a fork of the shell. So you want to make sure, if you want to change the current working directory of your main shell, you want to make sure that it runs in that actual shell process, not in a subshell thereof. If we run the cd command in a subshell, then that would be modifying the current working directory of that fork, of that subshell, not of the shell from which it was spawned. In any case, here's an example of using the cd command. Say here's my prompt, I'm user Brian, logged in on the system Ubuntu with the current working directory of /home/Brian. And so if I enter the command cd with an argument of /bin, then that's changing my current working directory to /bin. And you can see this change of directory in the next prompt. If I then enter the command cd with an argument of /, then that's changing my current working directory to the root directory to /. And so the next prompt we get displays the current working directory as /. An important thing to keep in mind is that when we fork processes in Unix, the fork, the child, inherits the current working directory from the parent. So any command we run from the shell inherits the current working directory of the shell itself. And this is significant because many commands will use the current working directory as a default argument for a file path when no file path argument is given. Like for example, the ls command, if we don't give it a program argument specifying a directory whose contents we wish to list, then the ls command assumes we wish to list the content of the current working directory. So in fact, if you run ls with no arguments at all, then what it will print out is the contents of the current working directory of your shell. The built-in command echo simply prints all of its arguments to standard out. So here, for example, we have echo with the arguments foo and 2, 3, 4, or 8. Then that simply just puts out to standard out the text foo and then space 2, 3, 4, 8. Now, of course, this may not seem useful at the command prompt because why would you want the shell to just spit back at you exactly what you just typed? But one way this is useful is that in various ways we haven't yet discussed, the shell, when we use certain special syntax in the arguments, processes the arguments such that what actually gets sent to the command is different from what you literally type. For example, the $sign specially denotes the syntax for what's called variable expansion. The shell, again, is basically an interpreter. It's effectively a programming language, and like in any programming language, we have the ability to assign values to variables. The syntax for this is to simply write the name of the variable you wish to create or modify, follow it immediately with an equal sign, and then everything that follows the equal sign is considered the value being assigned to the name. Effectively, all of the text that follows the equal sign is a string, and that string is assigned to the variable. If we then wish to use the value of the variable, we can't just refer to the variable by name, because if you were to just write the name, that name as text would be the argument, not the value held in the variable. So to actually use the value of a variable in the arguments to a command, we use the $sign and then follow that with the name of the variable. And depending upon the context, you sometimes will need to enclose to distinguish the name of the variable you're expanding from the text that surrounds it. So here, for example, we're assigning the value 4 to a variable named foo, and be clear here that though it's a number 4, the value being assigned here is actually a string consisting of the character 4. And then if we invoke the echo command with an argument of $foo, well, $foo gets expanded, or replaced we could say, with the value of the variable, which is text simply consisting of a single character, the digit 4. So what this echo command will actually print to standard out is just the digit 4, not a $, not foo. That gets replaced with the value. In the next line, we're again invoking the echo command, but now the argument is the expansion of foo followed by a letter D. And this time we have to use the form with curly braces, otherwise the shell would think we're trying to expand a variable named food, not foo, and so actually it would then expand to nothing. It's actually possible to expand a variable that doesn't exist, and it just expands to an empty string. So the next two lines, it should be evident what's going on. We're simply assigning the string hello to a variable named bar, and then the next line we're echoing out the content of the variable bar. So hello gets printed to standard out. You may recall earlier I mentioned there's a difference between single quotes and double quotes. When we use single quotes in the shell, what gets quoted is the text verbatim with no exceptions. Double quotes, in contrast, make a few exceptions, including the $sign used for variable expansion. So here when we echo $foo enclosed in double quote marks, the expansion is actually performed, and so it prints 4 to standard out. Whereas if we were to enclose the same in single quotes, then what gets echoed is the verbatim text, $foo. A variable in the shell could be marked as an environment variable, which effectively means that the shell creates a matching environment variable, and then when you subsequently assign new values to your variable, the matching environment variable is given the same value. This can be useful because when we fork our shell or launch other programs from our shell, we may want those forks and other programs to inherit certain environment variables. For example, the Python interpreter expects to inherit an environment variable called Python_path, which is a list of directories which the Python interpreter then uses to look for modules. So before we launch the Python interpreter from our shell, we want to make sure that the shell itself has an environment variable Python_path with an appropriate value. Now, by default, when you create a shell variable, it is not an environment variable. We have to mark it as such with the built-in command export. So here, for example, we create a variable foo, which we assign the value 8. And then in the next line, the export command is marking the variable foo as an environment variable. So it actually creates here a matching environment variable called foo with the current value of the shell variable. In the next line then, when we assign a new value to the shell variable, this variable is marked as an environment variable, so the matching environment variable is updated with this new value. As I've been saying, the shell really is just a kind of programming language, and so we need control flow constructs, and for that purpose then we have the built-in commands if and while. In general, these both work like their counterparts in languages like Python and JavaScript, but their precise syntax is a bit eccentric owing to the command-based nature of the shell syntax. So looking at the if command, for example, the word if itself is a built-in command of the shell, but unlike the commands we've seen so far, where the arguments are basically just a series of strings, if expects as its arguments first a command list, followed by the word then, followed by another command list, followed by the word fi, which is if spelt backwards. And the while command has the same format, except the terminators are the words do and done. I guess it was decided no one wants to type ELIHW. Frankly, I find the idea of using the command name reversed as a terminator quite silly. They should have just gone with done for all terminators, though I personally would have gone with end as the terminator for every if and while. Also, I should remind you here that the last command in a command list must be terminated either with a semicolon or a new line. So as you see them written here, where if and while are both portrayed as single line commands, these command lists must all be terminated by a semicolon if they're going to be on the same line. They can't just be separated by a space from then, do, fi, and done. In any case, what's going on with both of these commands is that their first command list is the condition, and then the second command list is the body that executes. So the condition command list is executed, and if its exit status is equal to 0, that is considered true, and anything other than 0 is considered false. Be clear that this is actually backwards from JavaScript and Python, where 0 is considered false and all other numeric values are considered true. Oh, and I'll also remind you that the exit status of a command list is the exit status of its last executed command. So if a command list does in fact consist of multiple commands, it's the last executed command whose exit status is used as the condition. Last thing to mention here is that though I do show these two commands written out as single lines, in practice you'll usually see if and while commands written out on multiple lines, just like you would expect to see in, say, JavaScript or Python. Because these commands are only terminated by the pre-designated words fi and done, you can use new lines to separate the commands in these command lists.